Advanced Programming Techniques for a CNC Milling Machine. This paper takes advantage of the powerful capabilities of modern CNC controllers such as subprogramming and parametrization to demonstrate the efficiency improvement of machining operations as a result of applying them in short, flexible, and smart CNC programs. To show the benefits of using the above capabilities over conventional G/M programming language, 3 representative applications are presented through manufacturing drawings, flowcharts, program lists, and simulation results. As it is deduced by all 3 cases, subprogramming and parametrization facilitates the full exploitation of the potential of a CNC machine and makes CNC machines easier to work with. Keywords: CNC programming, milling, parameters, CAN cycles, drilling, cutter path generation. 1. Introduction. The operation of a CNC machine tool is controlled by a program written in the G/M code programming language called part program. A part program contains an ordered sequence of statements specifying in detail the cutter motions to be executed and the auxiliary operations, e.g., spindle on/off, spindle speed and feed rate, to be realized by the CNC machine in order to machine a specified part. A statement is made up of words, characters, and numerical digits are the elements that constitute a word. For example, the statement. Each of the codes other than G and M has a unique function. The G and M have many functions depending on the following 2-digit number. These functions have been standardized and are commonly known as G and M codes. Generally, a G code, named preparatory function code, defines one type of motion or one mode of operation, while an M code, named miscellaneous function code, turns various operations on/off, e.g., coolant flow, spindle, etc. It must be noted that not all the possible code numbers are allocated, which means that control systems manufacturers can use those remaining for whatever purpose they wish. Parametric programming constitutes an innovative programming technique of G/M code programming language. This innovation is not well known, which is unusual because of the fact that it simplifies the CNC procedures dramatically, lessens the user's dependence on CAD/CAM and contributes to bare minimum cycle time 8. As production quantities grow, every second of program execution time becomes more critical. An important factor that minimizes the cycle time is how the program is formatted. While CAM systems have come a long way, it can be difficult, if not impossible, to cause some CAM systems to output CNC programs as efficiently as can be done with parametric programming technique. Applying the technique of parametric programming, a part program can be written using variables, arithmetic, and logic statements similar to usual programming languages such as BASIC, Pascal or C. The specific is that in the case of CNC programming, all these parametric expressions are used to represent the machine axis position feed rate, and spindle speed functions. Like other computer programming languages, parametric programming comes in several versions. The most popular are those of Heidenhain and Fanuc, Custom Macro B, Controls 9. Others include User Task, from Omirou, QRoutine, from Sotic, and Advanced Programming Language APL, from G&L. The present work uses the latest version of Heidenhain Control 4, called ITNC 530. The rest of the paper is organized as follows. Section 2 describes in detail the mechanism of defining and using parameters in the environment of Heidenhain Control. Section 3 is an analytic presentation of 3 case studies. Each case represents an application category. Namely, Case 1 illustrates the potential of subprogramming and parametrization to widen the motion generation capability of a CNC machine with interpolators other than the standard. Case 2 points out the flexibility of a parametric program to accommodate families of parts, and Case 3 shows how parametric programming can be used to invent new useful CAN cycles. Finally, Section 4 summarizes the contribution of the paper. 2 Heidenhain parameters. In the Heidenhain Control 4, parameters are designated by the letter Q and a number between 0 and 99. Using Q parameters, an entire family of parts can be accommodated by a single part program. In such a case, Q parameters are entered in the part program instead of fixed numerical values. For example, several parts may require machining a pocket, figure 1, with different sizes. A single parametric program can be called up to machine the specific feature. Prior to the execution of the parametric program, the numerical values for each pocket are transferred to the respective parameters. This approach eliminates the redundant codes in part program and substantially reduces the size of the program and programming time. Case studies. Complex motions, Serpentine curve. The case of a serpentine curve, figure 2, was selected to illustrate the mechanism of generating complex motion using subprogramming and parametrization. Figure 3 shows the flowchart at which the program of list 1 was based on. The same program can be executed to machine a serpentine of any size, at any starting angle, with any angle step and any milling depth. Simulation results are shown in figures 4 and Case 2, families of parts A bolt circle. Almost all companies have at least some applications that fit into this category. Possibly they have prints dimensioned with variables right on the print. The programmer must reference a chart on the drawing to come up with values needed in the program. Or even if they don't have a perfect family of parts application, surely they have at least some work pieces that require similar machining operations. With parametrization, it is possible the development of general-purpose routines for similar machining operations. Inventing CAN cycles. A spherical pocket. CAN cycles provide a programming method of a CNC machine to accomplish repetitive machining operations, using the G/M code language. Their use eliminates the need for many lines of programming, reduces the programming time and simplifies the whole programming process. 7. 10. All CNC machining controls come with a set of helpful machining CAN cycles. However, the standard CAN cycles are limited in number and capability, being unable to accommodate the needs of applications requiring something unusual, something that the standard CAN cycles can't handle. Parametrization and subprogramming comes to remedy this situation, by offering to the programmer the ability to invent and develop his own CAN cycles. The following work demonstrates the application of parametrization and subprogramming in developing a CAN cycle for machining a spherical pocket. A spherical pocket. The machining of the spherical pocket is achieved by repeating two successive motions which are programmed in a subprogram. These motions are a full circular polar motion on XY plane. For conclusions. Programming method is of utmost importance in achieving effective CNC programs regarding flexibility, programming time, and most critical to cycle time reduction. As it is demonstrated by the three representative case studies, parametrization and subprogramming techniques constitute a powerful programming tool in this direction. The generation of various motions with the desired each time accuracy, the development of programs capable of machining families of parts and the invention of new CAN cycles enhancing the feature-generating capabilities of CNC systems were all achieved by short flexible programs incorporating these advanced programming techniques.